Morning, everyone. We're going to talk today about a technique for defeating active interposers on the bus between the TPM and the CPU using dice to the rescue. My name is Jeff Andersen. I work on platform security at Google and also co-lead with Brian Kelly on the security project here at OCP. My colleague Jordan also works at platform security, and Ahmad on Microsoft Azure security. This work has had a couple of call-outs in previous sessions as Project Kirkland. Intel had an awesome demo of this technology using a physical Intel CPU talking to an Infineon TPM, so I want to give a great acknowledgement and call out to our excellent partners there. And we're excited to get into the whys and wherefores and how of this whole thing. So first we'll be talking about some attestation primitives that the TPM provides and how we use them in our data center environment, how they can be abused by active interposers. So we need a solution that is friendly to data center flows, and we leverage SPDM and dice for this. Some background for those not familiar as much with the way TPMs work and operate. So TPMs are a component on a machine. They feature PCRs, platform configuration registers, which are roll-forward like hash banks. And you can receive measurements over the course of a boot. How do you use this? Well, a CPU will boot several components over the course of boot. Start with some low-level firmware, run some BIOS, a bootloader, then the kernel, some other code. Each layer can measure the next, capture a cryptographic hash of that layer, and send it as a measurement to the TPM to store in those PCRs. And you can't roll those back, only forward, so by the time the boot is completed, the PCRs, if you've done everything correctly, are an accurate representation of the host boot configuration. Have things like, did we do secure boot? What kernel did we run? Things that a data center operator very much likes to know. Other primitive that the TPM provides is a policy engine, a very nifty aspect of TPM. Any TPM object, you can attach a policy to it. Policies, there are various different flavors of policy assertions, and they can be combined in arbitrary logical groupings. And any given policy can be computed into a unique hash. Every different policy will have a different hash, and the hash will appear in the public portion of a TPM object. The TPM will enforce that the policy is satisfied before it allows the object to be wielded. So how do we use policies for attestation? Well, the host can create a TPM object with a policy such as policy PCR, saying this object is only usable if the PCRs are thus, and then can attest to that object. The remote verifier can evaluate this object's policy hash, make sure that it likes the policy, that it likes the PCRs evident inside, and then once it's satisfied, can confer privileges to the host that are contingent upon its satisfying that policy. What does that mean in practice? Well, imagine that this TPM object is a sealing key. So now we can seal valuable secrets to the TPM. And we know, because we trust the TPM to enforce the policy correctly, that those secrets will only be available if the host is booted into the configuration we like. So yeah, this is a great primitive for attestation. Now, how might interposers mess with this flow? So there are a couple of things an interposer could do. They could passively monitor the bus between the CPU and the TPM. Now, if you are unsealing anything important or interesting, that would be evident to the passive interposer. This is mitigatable through things like salted sessions, which TPM does provide. But things get a bit more interesting, dare I say, dicey, if the interposer can now be active, can send commands onto the bus. So what can they do? They can modify your PCR extensions. They can drop them entirely, replace them with their own. They can allow the TPM to get all the PCR extensions and then just pretend to be the CPU and decrypt anything they want. A specialization of this is just to walk away with the TPM and work on your bench to your leisure, or at your leisure. We've been able to skirt around this in the past by deploying these machines in high security environments and doing things like soldering the TPM to the motherboard, burying traces, making it hard for an active interposer to do these nasty things. But these are changing. We're deploying machines in more and less trustworthy environments. And part of the reason why we're bringing this work here is because OCP has recently come out with DCSCM. I don't want to knock it. It's, modularity is great, but it does pose some challenges with interposability. Specifically, it makes it a lot easier for an attacker to do nasty things. We have the TPM over here. We have the platform root trust, have your boot media, all going over this very standardized and very easily interposable interface. I've read the DCI specs. I can, pinpoint. There's the SPY pins, eSPY, QSPY. They're all right there. What used to be a high skill operation now takes, $30 of hardware and a minute to pull off. So, not so good. Now, there is a platform root trust there, so does that solve anything or give us any benefits? So one of the common functions of a platform root trust in this configuration is to measure the contents of the BIOS SPY chip. So is that useful? Well, it's not a panacea, because as interposable as the TPM bus is, the boot bus is also interposable. So to paraphrase Morpheus here, are you really sure that that's the BIOS you're running? The BIOS that is measured in the SPY chip is not necessarily the same BIOS that ends up running on the CPU. Now, so there's some nastiness involved with interposers here. One might think, okay, can we take the TPM and move it into the CPU? Like firmware TPMs, are they a viable alternative? In some cases, that might be just the thing to do, but that is not the thing. That is not a widely applicable solution for a couple reasons. You might have regulatory constraints. If you need your TPM to be common criteria certified, it is a lot harder to do when your TPM is inside an SoC. Easier to do when it's a discrete part. The TCB of a firmware TPM can be larger than a discrete part, and a nice TPM implementation really likes to have some secure reroutable flash, which is not widely available in SoCs. So I mentioned before we need a data center friendly solution. There are a couple of ways to approach this problem. I wanted to just briefly talk about some of the constraints we put upon ourselves, what this end solution needs to look like. We must support remote verification, meaning the CPU is not implicitly trusted to do anything. The verifier must check the CPU's work at every stage. 2, we must support intentional TPM part swaps. As previously shown, the TPM is on a DCSCM card, which is going to be swapped between machines. So we can't be permanently pairing the TPM and the CPU together by burning fuses or anything like that. And we also want to do some minimal disruption to the existing TPM logic that's out there. There's a lot of code out there which is written to talk to a TPM. We don't want to have to re-architect and rewrite it all to get security against active interposers. We'd like to provide some transparent security. So over to my colleague Jordan to get more about that.
All right, thanks, Jeff. So Jeff mentioned that the TPM has this policy engine. So if we have objects like keys or sealed data, we can attach a policy to that. And then the TPM will enforce that you've satisfied that policy before it lets you use the key or unseal the data. So what we want to get out of this flow is we want some sort of policy assertion that lets us as the CPU authenticate ourselves to the TPM. So we say we are a specific CPU that holds a specific private key, and the TPM will verify that public key and then put it in the policy hash of the object, and then that can be attestable by a remote verifier. So a remote verifier can say, I'm going to seal some data, and only the person that controls this private key, for which I'm going to put the public key in the policy, can unseal the data. So how can we kind of get this primitive kickstarted on the CPU? So DICE is a great way for doing that. So kind of a traditional DICE hierarchy might look like starting with universal device, or unique device secret on the hardware. And so that uniquely identifies the CPU. And then we can get a device ID key that we can wield on the device, and then a device ID certificate that's typically signed by like a manufacturer CA during manufacturing. And then we want to mix in the IROT firmware. So we want to know what firmware the IROT booted, and we get another key out of that, an alias key, that proves I'm specific hardware running specific IROT firmware. And then generally in an IROT, we've heard a lot about Calyptra this week. In a minimal IROT in the CPU, we'll measure the first mutable stage of code that runs on the AP. So you would, again, permute the dice CDI, get an AP alias key, and that gives you kind of the hardware plus the first stages of boot that you can wield some private key to prove that, I am this CPU running this code. So we want to take this a little bit further. We got to the first stage of BIOS, but we have additional BIOS that's running, and we want to get to a point where we have a dice identity that proves we've booted up to a point, and then we can do some more complicated flows. So like in an initial boot block in BIOS, we don't want to be doing complicated key exchange and protocols with the TPM. So it's ideal to be able to continue to extend that dice chain until we get to a kind of a richer environment to do that protocol. So we want to introduce a spec that TCG has been working on and is close to their first publication on that, called Dice Protection Environment. And so this is basically putting a dice oracle in the IROT such that code on the AP can call it for services. So I can extend the dice chain. I can give you some measurements, and you'll derive a new CDI in the IROT. I can call sign with that current context, so whatever CDI is derived from all the measurements I've made so far. You'll sign data for me, so I can bootstrap other protocols. I want to be able to certify that key that I'm using, so I want the IROT to make a certificate for me and then route it back to its initial dice chain that we talked about earlier. And then I want to be able to revoke that context. So if I'm some stage of boot and I see that I can't contact the TPM for some reason, it's unreachable, or I can't for some reason verify whatever the next stage is, I want to tell the dice engine, don't let me use this key anymore until next reset. All right, and I'll hand it over to Ahmad to talk about kind of what is the protocol we're going to do with those primitives.
Thank you, Jeff and Jordan. Building on what my colleagues Jeff and Jordan from Google just talked about, so we are going to propose a solution that can solve the interposer problem, like extending fake measurements or like exfiltrating secrets using a protocol called SPDM. This is, you should think of SPDM as TLS for hardware devices. So it's a standard in DMTF. So in the SPDM protocol, you have two parties. One is the requester and the other is the responder. In this case, the TPM is the responder, and the CPU, the application code running on the AP processor complex is the requester. And both the requester and responder need dice identities, and as it was explained earlier, the CPU IROT alias, the CPU alias key in the application processor will use that dice certificate as a requester identity. And in the TPM case, we already have certificates like endorsement key and attestation key, but we are proposing a new key called the TPM SPDM identity key, which could be in theory based on dice, but it's still subject to discussions. And as it was called out earlier, we are trying to be minimally disruptive. So for the most part, there is little to no changes to the TPM stack. We are going to have a shim SPDM layer between the TPM software stack and the physical transport layer. And like 99.9%, both these, the TPM stack and the transport layer do not know about the existence of this SPDM layer, except for something called policy transport security we'll get to in a bit. And again, SPDM protocol as such is like a 100+ page document, but we are going to standardize a minimal subset of commands that is required for this flow. So a TPM manufacturer that has to implement, when it's standardized, will not need to implement the entire SPDM protocol. You could have something small. So the minimal set is like get version, capabilities like the TLS, something like TLS, negotiate the algorithms, exchange, key exchange to arrive at a session key, and that's pretty much it. So then, as Jeff talked about earlier, we have a very rich policy engine in TPM. So we're proposing to add a new policy type called policy transport security. So what policy transport security, the behavior of it is going to be satisfied only if the TPM firmware asserts that there is an active SPDM session. So if the TPM has been booted and the software does not, the requester does not establish an SPDM session, then if policy transport security is executed, it's going to result to false. And then if you're trying to do an unseal operation, the unseal operation will fail. The other thing that we're doing here is you're able to bind policy transport security to the identity of the requester. So you can say a verifier or a relying party, remote relying party can seal a secret to a specific TPM, and the secret is guaranteed to be unsealed only if there's an active SPDM session and it is bound to a specific CPU. Like if, for example, you expected a CPU from AMD, ARM, or Intel, but data center attacker swapped it with the Raspberry Pi, which is very insecure. You're not going to get the secret because the dice identity of the CPU manufacturer is enforced by policy transport security. Oh, okay. Okay, so summary. So what are we guaranteeing here using the policy engine and policy transport security and everything? The verifier is able to know that it's a legit TPM bound to a legit TPU with specific initial, the DICE certificate of the application processor code is also measured. So you know it's a legit TPM, legit CPU, and by the way, it executed this piece of code very early on boot, and that acts as the root of trust for the rest of the code that gets loaded. So it's demo time. So we have a QEMU demo set up here. So we've implemented a DPE emulated device, and then we've modified SWTPM, which is an open source CPM implementation with SPDM integrated. And we've modified the Linux kernel, TPM driver, and the Linux kernel with the SPDM requester. And this is an emulated demo, but if you need a cool physical demo with a SPI interposer and stuff, please stop by the Intel booth. They have a really cool demo up there. Okay. Oops. Oh, how does that work? Oh, crap.
You might need to fiddle with the port.
What do you do?
This is kind of finicky.
It's weird that it died right when we exited presentation.
No.
No audio.
Oh. Oh, there it is.
We're good.
Oh, we got it. Cool. That was good. Okay, so we're going to start off by running the DPE simulator.
Might want to pop
And then
font size.
font size.
I don't know, maybe not. Whatever.
I guess it's okay. Okay. Then we're going to run the fancy TPM simulator with SPDM integrated. And then we're going to run our QEMU with the custom compiled Linux kernel. So it's going to boot, and you've got the you've got the TPM traffic. We're just printing it out. So it's okay. I'm logging into my secure root account, which has no password. And then let's run a PCI read operation. So if you look at this, you get this here. So on the wire, if you look at a current TPM with a SPI interposer, you see whatever is here matches here. But in the fancy secure TPM that we are proposing, it's all encrypted. And if you run the same command over and over again, because SPDM has ephemeral AES keys with counters and stuff, it'll keep changing because it's encrypted. but the plain text remains the same. And we could do this for unsealed. I think on the Intel demo, you can also see an unsealed thing. So that's pretty much the demo. And we can get back to the presentation. Current slide. OK, thank you. Back to you, Jeff.
All right, so in summary, we're excited about this very standards-based approach. We have TPMs on one side, DP on the other, SPDM to bridge the gap. And these three powers combined have put a check on active interposers' threats they face or pose. So what next? Well, we want to obviously take this beyond a demo. So we need to get this standardized. We need to go into TCG, have that conversation. So if this interests you, please join us there and we can talk about it. Also, on the CPU side, we need to start developing and deploying IROTs that speak DPE to participate in this flow. One example of such an IROT would be Calyptra. So we fully intend Calyptra to be a standard open source implementation of an IROT that speaks DPE and will facilitate this flow. And with that, well, thank you for your time and see if there's any questions.
Comment and a question. The comment first. Next year we'll be celebrating the 20th anniversary of TPMs. TPMs have come a long way. SPY bus confidentiality was not an issue in the beginning. Now it has become in the last couple of years. Thank you for you guys tackling that problem and providing us a solution that is really nice and lightweight to implement. So really thanks. The question now. I have an architectural or conceptual struggle with the OCP architecture. In the SCM spec, the TPM is the SPY interface is both connected to the platform root of trust, as well as it goes out to the DC SCI interface. And we have CPUs, we have servers with potentially multiple CPUs. In your flow, you're talking about the TPM establishing a secure connection to the CPU. But on this architecture, the TPM physically hangs on 2 to 3 entities. So should I think of the TPM being, in terms of implementation, being able to handle multiple sessions to multiple masters simultaneously? Or where am I wrong?
So we do not intend to change the relationship, the one-to-one relationship between a CPU that boots code and a TPM that guards that CPU. As far as the other components that connect to a TPM, I think we're just exploring, right, this fact that yes, we have a platform root trust hanging off that TPM. The measurements it's providing, we're observing, are not as robust as the measurements that an IROT captures. So who knows how the hardware design will evolve based on this. I think it's early days.
Specifically to the point of like multi-socket systems, I think we have an interesting discussion to have in Calyptra and like other IROT discussions around what is the identity of a multi-socket CPU? Does it, like if it acts as one machine, does it have a single identity? Do we treat each socket as a different identity? So I think that's not fully fleshed out, and I think we should definitely have that conversation.
So follow up on that. Does the TPM have a specific role in the combination or in the connection to the PROT here on that SCM?
Not in this flow. We don't anticipate that.
Okay.
Yeah, we are not changing that architecture. It's still tied to the application processor. We might think about localities, but that's something.
So essentially, the TPM sits on the SCM, but it serves the CPU on the CPU board. And if there are, like on the Intel board or so, if there are 2 CPUs, then potentially we will have 2 TPMs in the end, wherever they're physically sitting then.
Right, relying on such a flow like this to make sure that they can't crosstalk. Yeah.
Good presentation, thank you. One of the question I have is, you mentioned about provisioning SPDM key to the TPM. Can you say a little bit more about when is that expected to be happening? Like, is it when you establish first session or manufacturing, or where would be the right time to provision that SPDM key? Yeah, that first one.
So the way we are thinking about it right now is the SPDM key is, TPMs come with primary seeds, like endorsement seed and storage seed. So we are going to standardize a primary key template with a specific flag. So you can do TPM to create primary like you do now with a specific flag. And once that happens, that key becomes the SPDM key. So you don't have to provision it, existing TPM flows. It's just that you need a specific flag in the create primary call. So it's not something you fuse in manufacturing. Does that kind of answer the question?
Yeah, I was trying to understand where in the process that key gets in there or created or whatever.
So as part of early boot or in the initial BIOS code, you could probably create the template and load it into a specific index. And then the TPM uses that specific, and it'll be standard index, of course. So it'll use the key wielded at that standard index to respond to SPDM requests.
And I will say that this is a point that we've debated, like even between the three of us, quite a bit. And I think, like as we go to standardize this in TCG, this will be a discussion point. So we're happy to continue this discussion. I think it's not set in stone.
Nothing's final, so it's just evolving. We have a cool demo, and we're going to take it to TCG with our friends at Infineon, Intel, and everyone. Yeah. Cool.
So this is Brian Kelly. So this was done on an Infineon TPM. So are you going to publish this and a source code ahead of the standardization in TCG, so other TPM vendors can leverage it too to bring it forward? Or are you going to wait to go through TCG, and how long do you expect that to take and evolve?
Yeah, so that's a tricky question. So we are definitely going to put the specification into the TCG format and take it down there. But I think we have to clean up the demo code, and if we are not like infringing on any TCG requirements, I think we do want to publish it into an open source repo, but we'll have to consult TCG. Or if there are no legal requirements, I think we should just be able to publish it.
So if somebody wants a secure TPM, they have to go to Infineon?
As of today, I guess, yeah, because they partnered with us for this flow.
Thank you.
So I had a question about SPDM, in particular, what version? And I'm asking that because having been involved with the TCG DICE activity and the transition from 1.2 to 1.3, if you weren't DMTF and TCG, you didn't necessarily have visibility into the specs until late stage, and of course, DMTF is continuing to work here. So this looks like it assumes a particular version of SPDM, and I guess I'm curious as to how you're going to deal with it going forward, especially if you're doing TCG work.
Right. So now SPDM wears a couple hats. It's great for like getting a tested measurement blocks out. That is a side of TPM we are not leveraging here. We are specifically focusing on secure sessions, which came out in 1.1 and got a bit cleaned up in 1.2. So specifically, this is targeting the SPDM 1.2. And if there are changes to that functionality in SPDM which require us to roll that version into the subsequent TPM spec, we'll have to cross that bridge.
And as we called it earlier, we don't intend to support the entire shebang of SPDM. We need a really small subset, key negotiation and identity and stuff. It is satisfied by the current 1.2 spec, but if there are more requirements in the future, obviously we'll look at the future specifications.
Thank you for the great talk. My question is, in this architecture, is it possible to change the CPU in the field or not?
It is. It is possible to change the CPU in the field. And the intelligent party here is, there are cryptographic evidences that get sent to remote verifier. So the field, you don't have to blow any fuses or anything because there's no hard binding. And the binding is enforced by the remote verifier in like the attestation service in our data structure infrastructure or something. So,
but the new CPU has different UDS, so different.
Yeah, that's fine. But all we care about is it's a different UDS, but it'll be certified by the CPU manufacturer. So as long as we trust that route, yeah.
To be clear, like all secrets will be lost, right? The new CPU can't get the old secrets, but you can provision new ones if the verifier likes the new CPU.
Yeah.
So I should probably ask this before. You were targeting the TCG to do some of this work. Is there a specific reason why you're targeting TCG, or would you prefer using another organization that might be a little more open, like, for example, IEEE?
Well, TCG owns the TPM specification, and we require changes to that to support this flow.
So a couple of questions, one leading to the other and building on some of the things that were just said about UDS. Okay, so you're talking about TCG DPE, right? Do you need all of DPE? Do you need a subset of DPE? Can you quantify
We
quantify
can't.
that?
Oh yeah, I do think we intend to standardize a subset of DPE, and we would like to publish a profile. So I think that will be forthcoming, and also a good place for us all to discuss in TCG.
And DP is not out yet, but we did get clearance to discuss its existence here. So.
Okay, excellent, right? And we were just discussing, TPM vendors and TPM stack changes, but the gentleman just asked, what about the UDS? That's on the CPU side, right? So what is the state of CPU support for this? What do you foresee? Where are things there? Because there are many CPU vendors.
Yeah. So we've been talking to a few partners. I think we don't have anything we can announce in the open.
Publicly on stage, but we are engaged with major CPU vendors. And
is it going to happen?
Yeah. I mean, I guess.
Yeah,
it's going to happen.
You mentioned that you modified the TPM driver in the Linux kernel. Have those patches been accepted?
So the doing this SPDM session in the Linux kernel was simple for demo purposes. I don't think we envisioned that the kernel be the requester in all cases. I think we still need to iron out where we want that piece to live.
A couple of things, right? So BIOS will need to change because one of the first entities that talk to the TPM is a BIOS. So obviously the BIOS stack is going to have an SPDM requester code. Then once the OS boots, the kernel, the TPM driver and the kernel will also need, but we're still working through the details. After that, when we get back to Redmond, Kirkland, we polish this up and we talk to the respective driver owners and go through the motions. But then as Brian pointed out, like, I don't know if we get to do that before the standardization or do we wait till standardization, so.
Hi, very nice work. Thank you for showing that. Couple of questions, follow up on.
I'm sorry, let me just, so we are at 9:32. We have a break from now to 9:40. We're happy to keep chatting, but yeah, that's so.
Yeah.
Okay, so earlier mentioned, I think from over there, about localities and how you address them. So with that respect also on HCRTM or hash sequence on locality 4 from the CPU to the TPM, how you envision of using that or incorporating that into. And early mentioned now with the driver, I assume, and you said that BIOS boot block would need to implement that. You would probably need higher levels of software and OS loader maybe, or OS itself.
Yep.
Each one to implement it by itself, and how you see that the secrets of the session are passed through one layer to another, or are you going to do verification of each layer by itself?
So the way we're thinking about now is, this is subject to debate, is the identity always remains at the IBB because that's where the dice key for the application processor ends. And each layer establishes its own session. It renegotiates a session. But then each layer is going to enforce cryptographically or that it's talking to the same TPM. We're thinking if it's like a normal comparison or if there's a challenge response. So that's something we're still debating because it's a separate session negotiated at each layer from like BIOS, bootloader, kernel, or yeah.
And as for your first question, it's a great point about localities. I think when you consider active interposers, localities kind of go out the window. Like locality is basically designed as, if you can talk to this specific register as filtered by the CPU, then you're good to go. So like that doesn't really help us when establishing a cryptographic identity. And then for the SHRTM, like the start hash, start data, or those pseudo commands, we haven't come up with a good way to protect those. Those aren't standard TPM commands, and you can't enforce policies on them or anything. So that's part of why we want to measure all of BIOS into DPE. So like if the sudo commands are called, in an early stage of BIOS, like in Intel bootguard or something like that, that's fine. Those can continue to go into the TPM, but we also have an interposer proof measurement in DPE.
Second factor.
Yeah, exactly. All right, thank you.
Thank you.